Hey guys, I hope all of you are very excited for today because I definitely am very excited. Today we are joined by Joyce here, who's going to teach us a lot about deep learning, and I hope all of you are very excited. So let's show this excitement to Joyce by commenting where you are tuning in from. So whichever city you're tuning in from, just drop your city name so that we can show Joyce that people from all around the world have come to watch her. So we have Mohammed here who's written you hello. So there's a lot of people writing hello. A lot of people want to talk to you, Joyce.
Cool. See a lot of hellos. Hey guys.
Mario is from Angola. We have a hi as well, so not just hellos. A lot of hellos are coming in. We want you to like write down which city you're tuning in from, so that we can show Joyce that people from all around the world has tuned in to watch her, show her brilliance in deep learning. Yep, we have a lot of hey Joyce. There's someone from UK. Um, we have someone from Ghana on who's tuned in to YouTube. Then we
Oh.
have someone from Mongolia. Um, we have someone from Uganda. I hope this is not making you nervous and is motivating you further.
This is fun. There's wow,
Okay.
people all around the world.
Yeah. People from London, people from Bangladesh. Adil is here from Santa Clara. Adil is my manager who's traveling right now. So he's here to support both of us. Then we have someone from Hyderabad, from Udaipur, from Egypt, from Texas, from Delhi. Okay. So I think she knows by now that everyone has tuned in from a lot of places. So I think we can just start with the live stream and give the viewers what they're here for, right?
Sounds good.
Yeah. Okay. So the world of technology around us is like developing so quickly. I just want all of you to take a second and realize that there is a voice assistant in your room who can understand your tone of voice, who can understand your speech, and then do things according to what you tell them to. And there are robots that are like now learning from their mistakes and then teaching themselves how to walk. Computers can like or your phones can look at an object and tell you exactly what the object is. So if you go back 50 to 60 years and then tell someone this, they will think you are probably talking fiction or it's some futuristic technology. But we are living in this futuristic technology, and there's one technology that has made all of this possible, and that is deep learning. It is a very fascinating space. There's a lot to learn, and it's clearly visible from so many people who have tuned in today. And we also have the perfect person to guide us through all of this. She's All Star Joyce Huang. She's an alumna of the prestigious Cornell University, and she has a ton of engineering experience. She has interned at NASA, she has worked as an ML engineer at Qualcomm, and she's finally started working as a deep learning engineer at Amazon Lab 126. She's someone who's very passionate about this very futuristic deep learning field and is here today to educate us more on this field and teach us something like a few tools from her varied book of experience in deep learning. So welcome to the live stream, Joyce, and we are very excited to welcome you to this family of all stars.
Cool. Thank you.
Yeah. Okay. So, yeah, we have more hellos. I hope all of you are very excited for this live stream. Okay, so let's start with before we start our conversation on deep learning, let's go deep and learn more about your story. How did you start and find your interest in this very niche field?
Yeah. So I first started getting to know about this field in college, and I started getting more interested into it when I was doing a lung cancer nodule detection competition. It's like a course competition. So basically, we can use computer vision to kind
Right.
of predict whether a nodule that you see in a 3D scan is malicious or not. So this is useful, right? And this is very exciting for the medical field. So I started getting into this and just exploring, why, how does machine learning enable us to do that, and what are kind of the research doing it, and then it just, went that way. So yeah.
So mostly you started developing your interest in this field in college, and then probably you didn't like prepare yourself for it. You just stumbled across it in some manner.
I think so, yeah, because I studied electrical and computer engineering in my undergrad. So I was mostly focusing on kind of computer engineering, computer architecture kind of
Mhm.
field. And then it just that a lot of the applications in ECE right now, such as digital
Mhm.
signal processing, is also
Yeah.
turning into kind of a field of machine learning because you get a lot of data and then you can
Right.
process it by analyzing the signals. So the lung cancer nodule detection competition was actually a competition from the digital signal processing class, which
Right.
is quite interesting because you started to notice that there are a lot of ML applications in so many different fields. Like right now, there's like in the medical fields, in the drug discoveries. So they're not just like pure science or pure analysis anymore, but you see there's so many applications and it can become very useful very quickly. Um, yeah, so after I graduated, I joined Qualcomm to do machine learning accelerators. So it's basically you do basically I just the career path is provided me with opportunities to further explore it.
Okay. And there's a lot more to learn for you, like in this field itself right now.
Mhm.
So are you fascinated by what's coming next?
Um, Yeah, I think a lot of them, like there's say autonomous vehicle is one big, up and coming, everyone knows about it. But besides that, there's also many different applications. For example, I think the one of the most exciting one is in the medical field. Like imagine we can have so much more efficient drug discoveries and maybe have a personalized drug because now
Mhm.
we get to analyze from your personal data and what is the best suitable drug for you. So yeah, it's not just all cool and fancy things you see on the street. It's there's also very impactful discoveries. It's also very exciting for
Yeah.
me, and I'm sure for the rest of the audiences.
It's obviously very exciting. I mean, there's a cool side, but then there's a lot of useful applications that we don't probably get to know, but it's very useful. So
Hmm.
yeah, it's a very exciting field, and I am very excited to learn more about it. So can you introduce us to this deep learning field? Like, what does deep learning actually mean? And if you could give more pointers on how it is different from machine learning, because they both are used very interchangeably. So if you could give us a comprehensive view around that, that'd be great.
Hmm. Yeah, I think well, to start with, deep learning is part of machine learning. It's a subfield of machine learning, and machine learning just refers to the broader like algorithms or models that is able to kind of provide some guidance for machine to learn. As long as the machine is learning somehow, it's this is called machine learning. Um, and then, so basically, machine learning will like parse data and then they learn from the data and then make decisions about it. So that's what machine learning do. Um, and there's a little bit of on the math side, right? There's like many different ways of ML, like nearest neighbors, um, support
Mm-hmm.
vector machines, PCAs. Those are all like kind of machine learning. Um, but deep learning specifically refers to the field where we use deep neural networks to perform such behavior. Um, Basically, if you draw the graph of the neural networks, as long as like it's more than three layers, we call it a deep neural network. The reason is we are kind of simulating the brain cell functions in learning. We perform like backpropagation and forward propagations to allow these cells to pick up some of the details of whatever problems you're trying to solve, and then it does the learning on its own. So that's kind of the idea of deep learning because you have many hidden layers in between and we don't exactly know, we don't really tell each cell that you have to do this or that. It just we throw a layer and then it somehow learns on its own, so that's kind of the idea of deep learning.
So it's like more hands-free in some sense. In machine learning, you have to guide the machine in some manner, but in deep learning, we just let it do its own thing. Is it
Yeah,
like that?
I think in some sense, in machine learning, we know exactly what we're doing with. Well, actually, that's not true. Machine learning just is the broader family of everything, and as long as it's learning, right? And then the deep
Right.
learning is the deep learning just that we don't really know exactly what's going on in each of the cells, each of the neurons. We just throw it there, put it there, and as of the state of art, the deeper the neural network is, it usually performs better. So there's can be hundreds of layers.
Right. So deeper neural network will give us better results, but it will be computationally heavy if I'm like I read about it a little bit. So there's a trade-off that we have to do or something.
Yeah, there's a trade-off. That's first, and then the second is we don't really exactly know what the neurons do. So there's no guarantee. There's you can like mathematically prove that, oh, this model is guaranteed going to 100% detect a human in the camera. Yeah, so it's hard to formulate that. And but yeah, as of now, because of some of the researches that the past researchers have done, usually the deeper the large neural network is, it performs better, especially in natural language processing problems. We get billions of parameters. It's huge. And then the reason why we're able to do it, and the reason why deep learning has become a popular term out of the machine learning field, is because of the computational power we have. Just like you mentioned, this is very computational heavy. And we cannot do this 10 years ago. Like, imagine you want to run a matrix multiplication and tons of matrix multiplication on your CPU, like Intel i5, first gen. Like, this is just not going to work, right? And now we have like NVIDIA GPUs 3080, and they are very powerful parallel processing computation resources, which is why it has enabled us to do deep learning.
Makes sense. Okay. So, guys, if you have any doubts regarding anything that she's mentioning, because like I am getting my doubts cleared, I'm asking her questions and then she's clearing them for me. But if you want your doubts cleared, you can just write them down in the chat and I will display it on the screen so she can answer it for you. Because it's a new field, so let's learn together and then, learn more. Okay. So you talked about neural networks there a little bit. So can we dive deeper into how a deep learning algorithm actually works and how does a neural network work? Like how does it make a machine think like a human? Like if you could give more context on that.
Yeah. So the network itself kind of arises from the idea of perceptron. It's simulating the biological network that we have in our brain cells. So the idea is that, like, for example, when you're learning something, right? You, as a kid, as a baby, you do something, and then you kind of learn to know that whether what you did is correct or incorrect. For example, if you hit a wall and your mom told you to not hit a wall, you kind of learn that, and then you propagate that in your brain, and then you fix your behavior to not hit a wall every time you pass through a wall. So it's kind of that idea. Basically, we perform something called forward propagation and backward propagation, and also gradient descent. So basic forward propagation is kind of you're making your initial guesses forward. It's yeah, you don't have any knowledge. It's randomly initialized. We have like this called weights and biases associated with each neuron. So these weights are initially randomized. So you just do a forward propagation, and then you make some
Right.
sort of prediction. And then at the end of the prediction, you compare that with your golden output, and then the golden output will tell you how wrong you are. So if you are very wrong, you will get this very large gradient, and the gradient will propagate back, called backward propagation, and then each neuron will get updated to their weights. Their weights will be updated, and you kind of do this back and forth loop to do forward propagation, backward propagation, and walking the gradient descent to optimize further. Um, yeah,
Right.
basic gradient descent is an optimization algorithm. There's many ways you can do gradient descent. Or optimization. So this kind of the general idea of the kind of the
Mhm.
basis of the neural network.
Okay, that sounds very exciting. I mean, there were a lot of new terms for me, so I hope I can like read up about all of them. But I got the sense of what you were telling, and I'm pretty sure the audience got it as well. So if you have any questions, you can drop them down. So we have got a few questions. We'll take a few of them right now. Um, okay. Hmm. Right. So one of them we have is where can we use reinforcement learning in autonomous driving systems? So if you have any idea on this.
Yeah. So reinforce reinforcement learning is kind of a out of my area. But I think RL is also very exciting because it is used as training in a more in a scenario where you have more unknowns, right? And then you can kind of do this search when you have to explore every path, but you're not guaranteed to explore every path, which is also kind of a problem if you want to exactly apply it to autonomous driving. Because in autonomous driving, you want 100% of the safety. You want your algorithm to be rigorous. Um,
Yeah.
and I don't know if there's any like more state of the art ongoing research in terms of applying RL and autonomous driving. But as far as I know, I feel like RL is a little bit hard to let it just freely learn for autonomous driving because of you cannot prove its rigors, um, and it's it will probably serve as more of a guiding system than actually guaranteeing 100% or 99% of correctness.
Okay. I hope you got that, Arvind. If you have any further questions, you can let us know. Um, so Mayur asks, what is the first step to learn deep learning? Like, what was your first step, and what are the first steps that they can take?
That's a good question. I think if you get to take a chance if you get a chance to take a class in college, that's definitely one big resource to learn from. But if you miss that chance, there's a lot of online resources, and one of the most famous course is it's called Deep Learning AI on Coursera. It's taught by Andrew Ng. He's only one of the most famous AI practitioners in the field. It's a professor from Stanford, and the materials that he has on Coursera is exactly the class that he teaches at Stanford. So it gives you kind of it went through kind of the foundational math, like the forward and backward prop, and it goes through the hyperparameters tuning optimization. So it's kind of an end-to-end place for you to learn the materials and be able to get some hands-on work on it. So I would say that's a good first place to start.
Okay. So we will probably. It's on Coursera, right?
Hmm. I
Okay.
think it's one of
Cool.
the link that I recommended and sent to you before.
Yeah, yeah.
You can feel free to send it to the audiences.
Sure, I'll do that. Okay. So another question is how tough it is to learn this. That's another thing that people want to know.
It's actually not very hard. I would say it's very easy to get into, and you know, it's really not hard to get into the field because the field is very broad. And as you'll see, and I'll also briefly introduce in the PowerPoint, um, there's many segments of it, and some of them focus more on the math side. Some of them focus more on the software foundation side, and
Mhm.
some are DevOps or just typical software programming. So and some of them are even like data analysis. So it's very broad. The entire pipeline people it's mostly Python and C++, but yeah, you can see like people ranging from writing Python to writing C++, and there's just so many different fields and so many different subfields, and how the many ways that you can contribute to it. Um, like as we are learning the deep learning, or as I was learning the deep learning, I find it very difficult, and it's a little bit hard to relate the knowledge and to imagine how you would do this in an industrial setting, right? Like, if I was optimizing for, say, KN, a hand recognition model, like, I don't imagine myself, doing this kind of algorithms tuning and changing of the model architectures in the field. And in fact, that we don't. There's just many fields. Like, we have to care about the speed up, we have to care about latencies, and there's like features. You kind of look at the data and select what feature is most important for the machine learning. And a lot of times ML, you get a lot of accuracy and you get a lot of good results. It's not because you design a very good model, like with rigorous mathematical proof. It's more like how you select the data and how you're able to extract the data and the features to let the algorithms more easily notice the patterns and the features of it. It's really not hard to get into the field. So, and then as long as you have, 1 foot in the field, it's easy to kind of get into it more and then explore the rest of the rest of the world.
Right. That was very interesting. Okay, we'll take one last question and then we'll move to the slides that Joyce has prepared for all of us to understand deep learning better. So I hope your answers, your questions, a lot of your questions will be answered there. If not, we'll take all of them later because there's so many. We'll not be able to do the slides if we keep answering questions. So I'll just take one last question. Um, okay. So Priyanka asked that is it true that one should learn MATLAB to understand machine learning or deep learning? Like, did you have to learn MATLAB?
I think right now the hottest programming language for ML is Python. Um, I think ML and Octave was it's a little bit, like, I know 5 years ago Stanford was still using Octave, but they've been migrating to Python, and um, Python is one of the most prevalent languages in machine learning because of how many packages that people built for it and how much open resource contribution there are in the community. So if you use Python, it's not only because you can be fluent in Python and write ML. You can also participate in the open source community and then contribute to it. And through this process, you'll get to learn, what kind of machine learning work that people are doing and be more engaged with the community. So I would, if there's any language that would suggest to, for deep learning, it would be Python. But also C++ is very useful because a lot of the underlying implementation, like such as ML compiler or just like convolutions and the ones that's wrapped under the APIs, those are written in C++. And the reason is because it is first compatible with the hardware, and then it is very easily optimized, and it's a very fast language. And as you can imagine, there's a lot of performance and latency demand in terms of the speed of ML algorithms. So yeah, Python and C++. C++ is kind of my personal favorite language, but Python is definitely useful. Yeah.
Like, if I've talked to any machine learning engineer, they mostly suggest Python, but this is like the first time that I'm hearing someone say that C++ is their preferred language for this. But I'm obviously like not an expert, and then Python and C++ will do. That's what you're saying, right? Like, they don't have to learn MATLAB, right?
Yeah, I personally don't write in MATLAB. But yeah, if it's like the ML, like the training and learning algorithm, definitely like Python. If you're interested in the underlying like convolutions and implementing, the operators yourself, then that's kind of C++ field. So yeah, that's kind
Okay.
of, yeah. Basically, you're right. There's mostly people doing Python because there's like
Yeah.
TensorFlow and PyTorch.
Mhm.
Yeah, so.
Okay, so a lot of people have asked questions about projects and then where can you practice. So we'll answer all of them later. So for now, we will go into the slides that Joyce has made for all of us, and then we hopefully will learn a lot more about deep learning here. Yes, I
Cool.
hope all of you can see it, and then very excited.
Cool. Thank you. Yeah, so I'm gonna introduce you guys to a kind of a subfield of in machine learning. It's called the embedded machine learning, and I think the goal for my presentation is to give you a brief introduction to this exciting world. I'm not going to bore you with mathematical details, and I'm pretty sure some of you have learned that in school, or some of you have not. So I'm just not going to get into that. But I've provided some of the resources, and I will point it to some of the papers that you can read about if you're interested in the in kind of the details of the models. But I just want to through this presentation, I want to introduce you to kind of the applications and the use cases and get you excited about the embedded machine learning field. Yeah.
Okay, let's go.
So, have you ever wondered, your mobile phone? I'm pretty sure all of you have some sort of smartphones or are familiar with it. And a lot of people are probably familiar with the voice assistant feature, right? So have you ever wondered, when you say, "Hey Siri," or when you say Alexa, or when you say Google, like why does it respond, and how does it process your voice and recognize what word you're saying and just respond to some sort of word to you? And it's not just voice assistant, right? There's also face IDs, fingerprint sensors, and those are also like machine learning use cases. And the fingerprint can just, after your first initialization of tapping a few times, and then for the rest of the times, it can recognize your fingerprint. And same way with the face ID. And one other embedded machine learning use cases is in the autonomous vehicle, because sometimes you don't want your data to be sent over the cloud and then come back to make a prediction. And you want your car to kind of process what is in front of you real time and very fast, right? So those are all kind of things that we live kind of normally with our day-to-day life now, especially in the sense of mobile phone. And with all these are machine learning technologies behind them. So what is embedded machine learning exactly? So embedded machine learning refers to executing machine learning models on a device level. And when I say device, it means say your smartphones, it can be your computer, your car. So those kind of a broader embedded machine learning idea. But specifically, there's also you want to execute your machine learning model on a silicon. So when we say SoC, like silicon on chip, those are when the industrial people usually try to offload their machine learning on a very small device level.
Mm-hmm.
So if you have some if all of you have some sort of experiences with deep learning, you will know things like Google Colab or the general like search engine recommendation systems, some sort of things like that. And those stuffs are typically what we refer to as a large scale system. And the way you do it is you kind of collect data offline, and then you send it over the internet, and then on the remote server with very high GPU capabilities, you do some sort of processing there, and then you return the result. For example, in search engine training, right? We collect many thousands, well, actually billions and billions of logs from all over the world, and we do this processing on a very high power GPU, and then we say like, oh yeah, when you say machine learning, the first result of the link should pop up as this. This is kind of a large scale machine learning. You're dealing with billions and billions of data. Your models are huge. Your model is like millions or even billions of parameters.
Right.
On the other hand, you have embedded system. So embedded system typically deal with very small models and very small systems. For example, when you say, "Hey Siri," right? Your data. Oops, my Siri just woke up. Your data is passed onto the device, and then it returns a result without going through this loop of sending over the internet and then process your data and then come back. So yeah. So why do we do embedded machine learning, right? If we can, with fast internet and we have fast processing powers over the GPU, like why don't we just do everything on a scale? So there's typically three characteristics of embedded machine learning. The constraints are quite different. So the constraints are usually we want a low latency system, we want it to be low power, and we maybe dealing with applications with privacy and security concern. For example, on the first one, when we have low latency, basically means real time. We want it to be very fast, right? When you're calling your voice assistant, you don't want to wait like 5 seconds after a response, or not even like 1 second. Like the timing of this and the processing power that most of these companies are talking about, like with milliseconds. You want it real fast. And the second concern is power. So your phone is always on standby when you're trying to call your voice assistant. And you don't want it to consume too much power just by idling your phone. You know, you don't want it wake up in the morning and then at noon you're like, oh, why is it 80% battery already? Because it's just trying to listen to me like talking. That's not good, right? So we want it to be very low power. And the third thing is kind of privacy and security concern, right? Especially nowadays, privacy has become really a big issue with a lot of consumers, and people are starting to notice this. And they're just more concerned when you're sending your data to over the cloud. First, there's like the networks, right? And then the third, you are sending your data over to someone else's server that can record your data and store it in their memory. And some people don't like that. They want it to be able to process on the device, especially with like personal and confidential data, such as like healthcare industries. So those are kind of a privacy and security concern, why that motivates this field of embedded machine learning. Is there any questions so far? Or?
Yeah, so we have a lot of general questions. If you have any questions on the slides itself, you can drop in and then we will take it. But if you want to take a general question as well, we can right now. Okay. Mm, yeah, so we got a question on can we use machine learning in telecommunications? If you have any idea on this field.
Yeah, yeah, we can definitely use ML in telecommunications, and the exact applications of it. There's kind of a lot, and then Qualcomm, you know, the company I worked for previously, they are kind of a big telecommunication company, right? And there's many applications that people are trying to do research on, such as, for example, like digital signal processing, right? You want like ML can be applied in terms of like denoising. And I think some of the fields are even doing like fancier things with wireless, you know, targeting where signals should go, and so on and so forth. So yeah, ML is definitely like, you know, one applications of telecommunications. So yeah.
Yeah,
Definitely.
that was very understandable. I hope it answered your question, Umraz. I think we can go forward for now.
Okay. Yeah.
Yeah.
So what are the challenges of embedded machine learning, right? There's mainly two. First is the memory. So typical embedded platforms are very small. Like for example, if a microcontroller, it's only around 100, 200, 100 to 300 like SRAM, which is the fast memory, and then you know, maybe up to 1 megabytes of flash storage.
Mm.
So this is not, you know, very this is not very, it's very much, you know, your PDF file for your textbook can easily go to 1 GB, 1 gigabytes, like let alone a machine learning model, right? A VGG, it's kind of one of the popular CV algorithms, is 138 million parameters. And then the typical BERT model, which is a language model, has 110 million parameters. And people have come up with like even bigger models with billions of parameters. And the second requirement is the latency requirement, right? You want to reach real-time latency with minimal hardware resources. And this is, and that like these two combined together, as well as like the power resource, becomes kind of, they kind of conflict each other, right? Like imagine if you have some of you probably have a PC enabled GPU, you can imagine like how much power it consumes, and you probably need a fan or two to like fan out the thermal. But when you have a really tiny chip, right, you want it to be low power and then low latency and with very small memory. That's just hard, right? Like I give a comparisons in these two pictures. Like on the left hand side is an NVIDIA GPU. You can see how big it is, and then on the right hand side is a Qualcomm Snapdragon. This is just how small it is. So their physical volume is you can see the big differences already, and then you just have to implement and deal with the challenges of embedded machine learning.
Right.
So I'm now gonna transition to some of the applications of embedded machine learning and how people have come up with models that kind of solved this problem. And
Right.
one thing to know is that I'm more focused on the model side for now, but there's also many challenges that people are trying to solve on a hardware level. So a lot of the embedded machine learning are kind of a hardware and software co-design because you wanted to kind of change the hardware and then you want to change the software that are optimized the most for each other.
Mhm.
So one of the most popular applications is visual applications. I'm gonna get into just a little bit of the math. So it's not very scary, but I think this is super easy for you guys to understand. But the visual application are mostly based on the idea of convolution. Right? And convolution is very efficient in processing and capturing 2D information. And most of our
Okay.
images are 2D.
Mhm.
Um, so convolution is kind of the idea of applying a filter through your input image and creating a feature map. So what this means is that the filter itself is some sort of let's say we call it kernel, and then it's some sort of functionalities. You can have a blurred filter, you can have a shift
Mhm.
filter, and then you kind of write a math representation of it. Um,
Okay.
and then you pass this filter through an image, and then your image is somehow going to become what you want it to be. and and then this is probably gonna be a little bit confusing, like who come up with these filters. Like famous people come up with these filters. Like I don't come up with these filters. There's like math behind it, but we kind of just take it as granted and use it and apply. On the right hand side, you can see that the original image, after you pass through a mean filter, it's going to be blurred. What this is doing is it's kind of taking the surrounding 9 pixels and then take an average of 1. So if you can imagine that those applications
Right.
apply to every kernel through an image, you're going to create a blurred image, and we're going to call the blurred image as a feature map. Um,
Right.
and then on the bottom, you can see, if you have a convolution kernel that's like a 1 on the left side, on the left middle, then your whole image is going to be shifted left by 1. It's kind of the characteristic of convolution.
Right. So, yeah, I'm like an ECE engineer, so I have like been through this convolution, and it's a little difficult to understand. So, like the way I understand it, and probably others can as well. So, we think of images as like images, but they're actually matrices, right? Like they're matrices of values. So it's like a matrix, and then you're multiplying it with some other matrix, so you get another matrix of some other values, and that is basically the blurred image, right?
Mm-hmm. Yeah. Yeah,
Yeah.
it's basically just transform one image into another. But through some of the math operations, you're able to kind of make it however you want it to be.
Right. So my education wasn't worthless. I mean, I have understood what
You
the
got something out of it.
yeah, I did get something out of it. Okay.
Yeah.
Cool.
Um,
You all have any other questions on this? You can drop them down, but I think we can go forward. Yeah.
okay. Yeah, I'm gonna show you some cool filters. So the first one's the original image, right? And then the second one, as you pass through a Gaussian filter, which is typically used as blurring, you get the middle image. And I think the Sobel filter is very cool because it's used for edge detection. So basically, when you pass in through the convolution kernel, you are able to extract the edge out of the images. So as you can see, these are very useful, right? For example, if you want to detect you know uh, the color of the shirt, and you don't want your ML algorithm to accidentally pick up the pattern instead of the shirt. Let's say someone is wearing a blue shirt with like vertical lines, and someone is wearing a blue shirt without vertical lines.
Mhm.
And then someone with a yellow shirt with vertical lines. You wanted to pick up the color and not the patterns on the shirt, right? So in that case, you can blur the image, as well as like some other applications. For example, in an architecture, right? We sometimes blur the image before we do edge detection because we don't want the algorithm to actually pick up, like let's say the textures on the wall. Once you blur it, you won't see the textures on the wall and you won't actually pick up the edges of it. So
Mhm.
that is why we kind of use this and then create a feature map based on from convoluting with the original image with like blur and edge detection.
Right.
So I hope that was understandable, and I hope that that makes sense to all of you guys. Um,
Yeah, I hope
and
it
this
did.
even a scarier image, but I'm just gonna go through this briefly with the this is a CNN. This is a convolution neural network, and you're gonna see this very common in if you work with vision models. So vision models typically have an input image. Like as you can see, we are trying to predict whether this image is a zebra or a horse or a dog, right? And as all of us
Okay.
can see, this is a zebra.
Mm.
So we pass this through some sort of models, and then we get an output. Um, and how we do this is we kind of pass this through convolution and max pooling. Convolution and max pool or pooling are, the most common basis operators of a CNO of a vision machine learning model. So through like convolution and pooling, you kind of extract out different features. For example, the first block extract out colors. There's black and white, and then the second convolution extract out some other more detailed information, like a zebra has like a pattern black and white, and then the third it kind of just extract out, oh, this is like kind of the mouth of the horse or the foot of the horse, and then at the end, so all of these convolution and pooling are called feature extraction, like feature mapping. They're not doing any like learning and well, they're not doing exactly any like learning and prediction.
Yeah.
But once you have all these feature map, you kind of lay them out flat. We call flatten it. So you flatten the layers and then stack
Mhm.
it so that you can. It's kind of just a kind of reshaping step, and then you pass this through a dense layer, which is a fully connected layer, where we actually do the classifications. So once you do the classifications, you can predict with the softmax the probabilities of whether this image is a zebra or a horse or a dog. So it's kind of like the whole model gonna look like.
So, just one question. Yeah. So we have a question from the audience. How many pooling can we make in CNN? Is there a limit or a constraint?
Um, in terms of like conv and pooling, you don't, but you can make it as deep as you want, right? It just depends on how many information you're extracting. There's kind of an optimal like the optimal number of it, but people kind of do it based on trial and error. It's well, the number of layers and the number of operators you select is called hyperparameter, and hyperparameter tuning is a big field of ML because you have to somehow figure out how much you want to use, right? If you don't want to extract it out too much details, and it becomes not useful. Like if you just extract the single pixel and pass it before the dense layer, then it's not very useful, right? Because you lose the information of the neighboring cells. But if it is too high level, too big, and too high level details, then you might end up only getting information such as like, oh, this image is some sort of black and white thing. Then how do you know it's a zebra instead of a crosswalk, right? So you kind of have to. So to answer your question, there's not really a limit in terms of like how many polling layers or how many convolution layers you can use, um, but you kind of want to train for it and select for it. Yeah.
Right.
So yeah.
Okay. Yeah, that's very understandable. So Raj has written here that I think like he's written it in Hindi that I'm not being able to understand what you're saying, but Raj, I assure you, I'm able to understand what she's saying. Okay, don't call me out like this. Okay, so just one more question. So in the fully connected layer, and because I want to understand it better, so
Okay.
like, how does the classification happen? So there is a lot of data that has been fed to the model or something, and then they are able to classify it according to that.
Yeah, so that's where the learning and machine learning happens, right? You kind of have to train it, and then the training can happen for a few days, and it does
Right.
this forward propagation and backward propagation, and then optimize to find the best weights in terms of prediction, and um, it's very interesting if you think about it. It's not very I think it can be intuitive to some people, but you kind of have to put in the idea of like forward and backward propagation and optimizations into the picture with the fully connected layer, and as well as the feature extraction.
Yeah.
There's optimal. We are training and making the machine to learn what is the best feature to pick up. So the whole thing we are training and performing learning on it and updating the weights and biases, right? So you kind of just pass through, and then at the end, so let's say if originally you have some model that predicts the input as a dog, right? And then your output tells you that you're very wrong, this is not a dog.
Mhm.
So it does the gradient descent back to subtract out the weights or to update the weights, and then we do it again. We're like, we
Okay.
still think this is a dog, but with less probability. Before it was like, I'm 100% confident this is a dog, and then it says like, no, this is not
Right.
dog, and then we do another probability, be like, I'm still 20% think this is a dog, and then you're like, oh no, you're wrong again. So and then the next time, like, is it a zebra? And you're like, oh yeah, you're right. So we get a plus, and then you kind of just do this back and forth thing to train. Um,
Okay.
yeah, on many images, of course, so that you can kind of tune it that to become more general.
Got it. I think I got it now.
I
Okay.
hope
No, like
that was
you explained it
better.
really well. You explained it really well. Like I was able to understand what you were saying, and I hope the audience was as well, because we're getting a few questions. Like Harshdeep asks, can we reverse this architecture to generate an image?
um, like in terms of like, you mean in terms of just from the output to kind of
Yeah.
reverse engineer the original image?
Mhm.
Um, it's a little bit hard, because the output I usually get is a probability of the classifications. Basically, at the end, like for this example, right, you have horse, zebra, dog, and you just have a matrix of, like say 0.9, or in this case, 0.2, 0.7, 0.1. That's like the final output you actually get.
Mhm.
Um, so it's a little bit hard, but it's in terms of like um so there's like two aspects I want to kind of touch upon. The feature maps itself, like the first stage, you see feature extraction, right? You would imagine it still contains some sort of data of the original input, and you're right. Some people can kind of reverse engineer out what the original input is, and this is a big security concern. This is like a big issue with like face recognition when you just take people's personal faces and put it through an image. But when you like send this models to the cloud, right, you still maintain this entire model, like from feature extraction to classifications, right? Like this is one dense model. Well, sorry, not dense model. This is one big model. And then um, some people can just take the feature extraction and then reverse engineer what the original input is, and
Mhm.
that's you don't want that. Yeah, you kind of don't want that. But on the other hand, there's another class of machine learning algorithms that can generate images based on, say for example, a text or some sort of input. So those are a different class of ML algorithms. Um, but yeah, that's I hope that answers your question.
Yeah, it does. I hope it does answer your question, Harshdeep. We can move forward for now.
Yeah. So I'm gonna kind of introduce you to a smaller class of algorithms that's for embedded machine learning. So MobileNet is one popular embedded ML or MobileNet, or like a mobile type of machine learning models. that was developed by Google. And MobileNet can do a lot of things. They can do recognitions. For example, when you move your phone camera to a QR code, it's able to draw a box around the QR code, right? So MobileNet can do that. It can also do object detection, like landmark labelings, etc. So this is very useful, and I think they have deployed this to one of the Pixels, Google Pixels, their phones. So the MobileNet is one example that people come up with to reduces the number of parameters to do specific applications, like more specific applications and less intense applications. And the way they was able to achieve this is through changing of the model architecture. So they kind of come up with this depth separable convolution idea, which is, you can kind of imagine it as you are factoring out the convolution, because convolution itself is a very expensive operations for computers. Imagine you multiply every pixels, and you multiply again, and you move it, and you multiply again, right? Like, this is very expensive. So a lot of people have targeted speeding up this specific operations. So depthwise separable convolution is it's like one way that you can change the model architecture to reduce the number of parameters. And I've attached kind of the paper you can read about depthwise separable convolution on the MobileNet version 1 paper. And I think there's 5 versions of it right now. They keep trying to make it smaller. And the first version of MobileNet was able to reduce to 4.2 million parameters, right? Like, as I mentioned before, a VGG16 has 138 million parameters, and the MobileNet only has 4.2, and is able to, achieve the same accuracies on ImageNet.
Right.
So another application is a very popular one in embedded machine learning is audio processing. So audio processing is kind of still very hot in the research field because there's so many ways to do it, and the data itself is not as well represented. It's not like just a 2D image and you can capture every information. It has this idea of the time domain, right? And usually when we deal with ML models with time domain, we use a recurrent neural network. So I'm also not going to go into details of what these things represent, but I hope that you can see, from this image on the left-hand side, you have this feed backward loop. Your previous output is feed into the next time step. And that is how the recurrent neural network is different than the CNN. It's not just like flat, without time domain data. But some of the more famous ones, besides some of the most famous recurrent neural network like RNN, LSTM, long short-term memory, and also GRU, gated recurrent unit. Those are also some popular recurrent neural network that you can kind of dig into, and if you're interested. LSTM is a very interesting one. It's able to let the model read a sentence idea. So with simple RNN, you are able to do speech recognition, right? So I have an example model that is trying to detect like 8 keywords, and it uses 1.6 million parameters. And how your device is able to recognize what you're speaking is at first how the model first kind of detect the raw audio and then record for a certain period, right? So if, say, your phone kind of listen to your wake words, say, oh, this is kind of similar to the person calling me, like, hey Google, then it record that, and then it kind of does processing on it, and it tells you, oh yeah, it is calling me, hey Google. And the reason and how it's able to do this is takes a raw input data, do a Fourier transform to a spectrogram, and then it does RN or some sort of predictions on it. So speech recognition is a hot field because it's just that it has to satisfy every constraints of an embedded machine learning. It has to be low power, it has to be low latency, and it has to work on the chip. So there's many ways that people have able to optimize it. For example, you only optimize it for one specific keyword, and that is one way to reduce the size of it. So we can easily get to an as small as, a few kilobytes, 20 kilobytes, if you just wanted to have one single keyword, right? And that is also the reason why your voice assistant will only respond to one name. It's not going to respond to other names.
Mhm.
Because the model has already been trained on a specific keyword.
Okay.
Yeah. Um, yeah, and I'm just gonna show you kind of a general machine learning pipeline. So data generation, model training, and model deployment are kind of the typical ML pipeline. But for embedded, um, you kind of want to add a stage of model validations on hardware, because our embedded devices, a little bit different here and there. Um,
Right.
so I think to just do the previous questions, how hard is it to get started or get into this field, right? All of these four stages have have thousands and thousands of people working on them, like on a team such as a Facebook, data, you get 20 engineers on the team working on it, and you get
Mhm.
you get one team supposed to working on data, and then you get a team supposed to work on model training. So there's just a lot of people working on like each stage. It's just not one person's job to do like from the end to end. um but I think this part is like, I hope this part is easily understandable to you, like how model is getting trained. You first
Mhm.
generate the data, and then you train the models, and then you do the validations on the hardware, and then you do model deployment, right? And the beginning stage, you gather data, and then you kind of clean up the noises. You do some sort of augmentations, and then to prepare the data. And after you train the data, as we just said, you can select a model architecture such as a CNN, RNN, and you do backward and forward propagations and to train the model, and then you evaluate and validate the model. Once you have a mature model, you want to deploy to hardware, and then the hardware, there's some sort of stages in optimizing compiling for the hardware, right? So there's ML um, compilers such as like Apache TPM that is able to optimize for the hardware, as well as you maybe want to consider something such as quantization. A lot of the embedded machine learning devices does not support like say 64-bit floating point computation. Maybe it just support like 16-bit or 8-bit quantization computation, right? In that case, you want to do quantizations to make it work on the hardware, make it compatible with the hardware.
Right.
And in the end, you can do model deployment and deploy to productions and kind of monitor how the model performs.
Yep.
Yeah. So for the models I just mentioned, they're very small and they are very easy to try, and they're simple and small enough for you to kind of just train on your laptop and for yourself to try. And I've provided some of the common resources where you can take a look at a very small model, such as like TensorFlow Hub, TensorFlow for mobile and edge. They have all the mobile nets that you can try to deploy. And then the
Mhm.
platforms I recommend, like first is a Raspberry Pi is one of the platforms you can get started with. It's very easy to use. It's a Linux-based platform, and it has a lot of functionalities and tutorials online you can just follow. So if you ever want to get your hands on, embedded machine learning models, like those are some of the resources you can try.
Right.
I think that's it. That's end of this presentation. I hope you guys get something out of it, and if not, I've attached some of the resources. Um, if you think this is like too shallow, you can dig into the papers and kind of learn about all these kind of cool stuffs.
It was obviously like it was very informative, and then me personally, I learned a lot, and I hope the audience did as well. Obviously, you can't like take lecture on each and every single topic, but the way you introduced it to all of us, I think it was very interesting, and then I definitely want to learn more about it. So we have a few questions on the last part that I would love to take up. The first one would be, okay, are the convolutions used same for similar type of ML applications?
Um, I'm just saying for convolutions itself is kind of a way to extract out the features, and the underlying operations of convolution is the same, right? But in that sense, there's a lot of parameters for convolutions you can tune for, such as the size of the filters. Like in the beginning, we might use a bigger size, and at the end we want to use a smaller size. But yeah, in that sense, say an ML application for computer vision, right? You can use convolutions to extract out some of the 2D information. So their use cases is kind of the same. Um, and I think convolution has now been able to, people have been using it for also time, like a time domain use cases, such as like audio networks. You can also use convolution for it. And I think, for example, like one of the YAMNet, that's also audio speech recognition net, and it also uses MobileNet's depthwise separable convolution. In that case, I'm not sure exactly how the convolution is applied to, the the audio files itself. I would assume it's being applied to like a spectrogram or some sort of 2D data. Um, but yeah, convolutions can, the primary reason, the primary goal of a convolution is to extract it out some sort of 2D information.
Right. Cool. I hope it was understandable, Rucha. If not, you can let us know with further questions. And I'll take one more question and then we'll move on to the other questions that we have. Um, so, is there any embedded ML models for analyzing Wi-Fi or Bluetooth? Are you aware of any of them?
Analyzing, I'm not sure about Bluetooth. But for applications in Wi-Fi, there's definitely, I think there's definitely many still ongoing research in terms of the ML applications in Wi-Fi. Um, for example, like securities applications, like targeting Wi-Fi's, and also such as like denoising and getting the strongest signals. Those are common ML applications. It was typically a DSP applications, but DSP's applications can, a lot of them are now being applied as machine learning, or being called as machine learning. The math kind of behind it is kind of the same, but um, it's just that we are able to leverage what we used to do with digital signal processing with machine learning, because of the abundance of data that we are able to collect. So I'm not sure exactly about whether there's any embedded models yet. I think embedded models, as far as I know, are typically used as like a vision or audio recognition. Yeah, so I'm not sure about embedded machine learning models on the Wi-Fi or Bluetooth part.
Okay, cool. So we can move to the next question. That is, deep learning is already a very advanced and futuristic technology. But according to you, what lies? Okay, I'll hide the slides because we don't need it anymore. Right. So, but according to you, what lies ahead? Like, how can it be used in futuristic applications? And are there any exciting developments that you're aware of what's coming next in this field?
Yeah, I think as I said, like healthcare, drug discoveries, autonomous driving is all the
Right.
upcoming exciting developments. And I think especially like one thing that's kind of exciting, but it's probably not going to happen anytime soon, is the power of quantum computing. Because quantum computing kind of have a proof of concept of how much computation power it can provide, and with that amount of computation power, we can do even more exciting things with deep learning and machine learning. Um, I think that's just a very cool field to do, to get our deep learning
Right.
going further. And we don't know what kind of development it's gonna come after. What kind of developments will come after quantum computing becomes a thing, or when we have 10x or 100x more computational power. At a time we're able to analyze more things, able to analyze more data, and the application of it is just beyond our imaginations.
Right. Okay, that was very interesting. I mean, I'm very excited for the future that's about to come. And okay, so I'll take one or two more questions from the audience and then we'll ask one final question and we'll conclude the live stream. So if you have any other questions on Joyce, on her work, or anything in general as well, you can ask them right now. So one of them is, can you let me know step by step learning approach to get job in India? But like you can obviously give a general answer to what kind of skill set they should work on, and then how should they start basically.
Yeah, so I think I always hope if you have some sort of projects, doesn't have to be overly complicated. One of like you would think, where do I get started with my project or train a model with data sets, right? One of the biggest platform that has a well-defined problem and the data set provided to you is called Kaggle. Uh,
Yeah.
yeah, I think many of you probably know it. But Kaggle has all sorts of data set and a very well defined problem, and there's also like tutorials or posts that people just write about. It's kind of, I don't know if you guys all know, you guys probably all know leak code, but it's kind of the leak code for for machine learning. People write submissions and they have provided problems for you and stuff. So
Right.
that's kind of one place where you can get started with projects. But on the other
Mhm.
hand, the software foundation is also very important. Like as long as you have a solid software foundation skills, um,
Mhm.
they can get you anywhere. Like Python, C++. Um, I don't know about India, but here in the States, there's a lot of company hiring for people with C++ skills in machine learning field because of the widely applications in C++. But also as well as Python, but usually with Python, you also want to know about the math and the model architectures of it, more than just the software foundations of it. So
Right.
basically, you know, be familiar with the programming languages and do some projects to get started.
Okay, so that generally progresses to the other question, that is, what are wait, it was right here. Yeah, what are a few projects that you worked on while learning? So few easy projects that people can probably try to emulate um, on deep learning or machine learning.
Yeah, so the two most famous like get started projects is house price prediction, and then the second one is handwritten digit recognition. So those are the typical first step projects, right? And then for me, I guess when I was learning, the computer vision lung cancer nodule detection was one of the projects that I worked on, and then I've worked on another image processing algorithm called the scale invariant feature transform. But that one I was working mostly on hardware software co-design to design a hardware accelerator for computer visions. Um, so yeah,
Okay, so handwriting. What did you say? I mean, I don't
the
think I completely got the project.
handwritten digit recognition. So basically,
Okay.
like people write like numbers, say like on a check, right? And then you
Okay.
feed into the ATM, and you want to recognize what digits that they write.
Okay. Got it. Yeah, that sounds like a very exciting project, and it almost sounds like I'll not be able to make it. But you labeled it as like the first thing that people do, so yeah.
It's very simple. It's like kind of a 3 hour project if you just follow
Okay,
tutorials and stuff. It's pretty fun.
I'll try it out, and I'll approach you if I have any problems, and other people can also approach you if they have any
Yeah,
problems,
sure.
right?
Yeah.
Okay, cool. So you have Joyce's permission to DM her on LinkedIn if you come across any problem. Okay, then. Mm-mm-mm. Okay, so do you think artificial general intelligence slash strong AI will be possible anytime soon?
Um, I mean, it's kind of a hard question. You never know what kind of someone just find some really cool discoveries, or have we somehow are granted a bunch of computational power. Um, but as of currently, the technologies that are mature, it is
Mhm.
a little bit hard. Um, like imagine, like for example, house kitchen or house robots is kind of a it's kind of one thing that a lot of startups in the states are doing. Um, you as a human can imagine, oh, I do dishes or I mop floors. I can watch how who's coming to my house, house securities and stuff, right? And if you look at the market, right, you get a robot that does specifically one thing. You get a robot that can only vacuum. You get a robot that can only watch the door. Because it's just so hard to generalize a model to perform different tasks. And it's also an
Right.
ongoing field of research. Like you can imagine if I just wanted to create a robot that cleans the bathroom, right? For humans, so easy. You like replace the toilet paper, you take out the trash, you kind of like sweep the floor real quick. When you see there's like some sort of trash on the floor, you pick it up, right? And then if you want to formulate that as a machine learning problem for a robot to do it, you have to like first like being able to maneuver the robot, and then second like recognize where it needs to be cleaned, and then you have to just recognize the precise locations out of the images to do the replacement or do like flushing down the toilet. It's just so hard for machine learning algorithms to do that, to have a more general tasks and being able to do that well. So,
Right.
but I would say probably in 10 years, not so long later, I feel like this is gonna become realities.
Right. So one last question from the audience: how did you get an internship at NASA? I'm also very excited to know about that.
I just applied and I got in. There's not
Yeah.
really exciting stories behind it. But yeah, I worked at the telecommunication department, and I worked on optical communication with like satellites stuffs. So cool.
So the answer was apply. That was the answer.
Yeah, I wrote a resume and put it online. Yeah.
Cool. Thank you so much for the very detailed answer. I mean, that's the solution, right? Like, we just keep thinking that we'll not be able to get something, but maybe the only thing stopping is just the application. And if we do it, then maybe we just get it. So, Joyce here is like an example. So, just apply to wherever you want to. Apply to NASA. Yeah.
Yeah, you can do that.
Okay. So, like, one last question from our end. I'm pretty sure people here have learned a lot, but if you had to give like your top three advice for someone who will start or has just started with their deep learning career, like what would the top three advices be?
Okay, three advices.
Yeah.
Um, I think the first one is to not forget your linear algebra. Those are very important. Linear
Okay.
algebra is very important, and if you are pursuing this field, you're going to see this again and again, and also
Mhm.
probabilities.
Right.
So that,
Okay.
speaking from personal experiences and the pain of having to relearn all the knowledge and the probabilities. Um, so yeah, and I think the second one is you can continue to do some, just expose yourself to the kind of the machine learning field, and
Right.
that's like online newsletters like deep learning AI like send out I think weekly, or I don't know, like daily emails, probably like weekly emails. That's enjoying wrote them, and then he kind of introduces what are the current ongoing researches, and or even any like issues the AI are facing. And even like podcasts, like one of my favorite podcasts is called Practical AI. It's on Apple Podcast. And it's very easy to understand. It doesn't go into any, like, it doesn't bore you with any of the math details, but it just tells you, what are kind of ongoing researches and how do people achieve it in a very various different fields, like such as like music generation, like how do machine learning just write songs, and like drug discoveries is the most recent one that it talks about like drug discoveries, and it's
Right.
very interesting, and I think it like touches upon people's life and for you to understand. um and I think the
One
last thing
more.
is,
Yeah.
huh?
No, no, one more advice. I was just,
Or-
yeah.
yeah. Yeah, I think the last thing is that it's also kind of a like something that I'm pursuing myself. That when you're able to learn machine learning and become impactful and contribute to whatever you're working on, just to keep being passionate about it, as well as you want whatever you're working on to be contributing to the society in a greater good. There's just so many ways that you can misuse this, with the
Yeah.
power of knowledge and with the power of the technologies you created and you are being part of, you want it to be contributing to the greater goods of societies, and
Mhm.
you anything that's like you want to like bring equalities, you want to bring diversities, instead of like harming other people and then use it as against others. So I think that's one thing that's very important to keep in mind as we are learning more about it and being discover the powers of it.
Basically, with great power comes great responsibility, right?
Yeah.
That's what you said.
Good way to put it.
Okay, cool. I think that concludes the entire live stream. It was a very exciting one. I learned a lot, but most importantly, I realized that there's so much to learn. So I'll go and read up more and then research more. And all of our audience members who are asking questions, I'm pretty sure they're also going to go and research more on this. So all of you can probably uh, drop messages to Joyce if you really enjoyed the live stream. I think she'll really appreciate that. And then I thank you, Joyce, for taking time out of your schedule to actually come here and teach a few things about something that you're passionate on. And I was very excited and very happy to talk to you.
Oh yeah, same here. Pleasure is mine. Thank you all for joining.
Okay, I hope all of you enjoyed the live stream. You can go and text Joyce on LinkedIn or connect with her if you really connected with her in the live stream, right? So I hope you all have a great journey with deep learning, and that's all from our side. Okay, bye. Bye.
Thanks all.